Good afternoon, everyone. This is Mr. Couple, and today I'm with my physics class, the ninth grade physics class, and we're going to be learning about electric vocabulary words like that have to do with circuits. So we'll be talking about electric current, voltage, and resistance. The three main ideas for this lesson are just the definitions of those three words. So current is the flow of charge due to a potential difference. A voltage source or battery can maintain a steady flow of charge. And then lastly, electrical resistance measures the obstruction to the flow of charge. So we'll be starting off by looking at examples of charge flow. So understanding how, like, the goal is that we want to be able to understand how we can harness electricity and get it to do work for us or to do things for us. So we want to take this concept of electricity that we've been talking about, charging a balloon on your hair or like lightning strikes. We want to actually do something with it. So in order we can so the goal today is I'm going to try to explain to you guys how we can actually harness this energy to actually do useful work for us. So the first thing I want to look at is just examples of charge flow. So I have this video of my son when he was, I think he was like 3 years old, and he slid down, or maybe he was 2, but he slid down a slide. And so check this out.
Okay, touch my finger. Touch my finger. Whoa!
So he slides on the slide, he gets charged up, and then there's an electrical discharge between us. So current is flowing between us, or charges are flowing between us. We call the flow of charge, we call that current. Likewise, we also see current anytime there's a lightning storm. Wasn't there just like lightning the other day here? I can't remember. This is from the I gotta give props to this. This is from the YouTube channel called the Slow Mo Guys. This is a slow motion video of a bunch of lightning strikes that they recorded down in Florida. So I'm just gonna let this play. All right, I guess we get the idea. One of the things that's really cool about lightning is that it actually forges its own wire through the air. And so it's constantly looking for a conductor where it can just dump all of its energy out to. And so that's what you're actually seeing here when you watch these little things come out, like these little feelers that come down. Like those are actually little like wires, like little forged wires that the lightning has like ripped electrons off the air, and it's searching for the ground. It's searching for a place where it can just dump all the charge to. Okay, so when you talk about charge flow, so how much charge is flowing between our fingers? Like when my son and I touch fingers. So it turns out it's like a micro coulomb. It's a very, very small amount of charge. But with a lightning strike, it's 15 coulombs. So 15 coulombs might not seem like a lot of charge, but that's actually a ridiculously large amount of charge. So down here I have the what a coulomb of charge is. So a coulomb of charge is this many electrons worth of charge. I'm going to zoom in on that. So 1 coulomb of charge is, I don't even know how to say that number. So there's 1,000, million, billion, trillion, quadrillion. So it's whatever. It's a ridiculously huge number of electrons. That's 1 coulomb. So if you want to talk about what a coulomb of charge is, it's a really, really, really large number. So that's the standard unit that we use. And so remember, the way that physics always works is when we define these standard units, we want to choose units that are roughly human scale. And so that's why you end up getting this like ridiculously huge number for a coulomb. Like if you want to talk about a lightning strike, that's just 15 coulombs of charge. And that's because electrons have a really, really small charge. All right, now if you want to actually calculate the current, it turns out that when my son and I touch fingers and there's a little spark that jumps, or if you like rub your feet against the carpet and you touch a conductor and then it sparks, it's a really, really small amount of current. So what's that? That's like 10 billionths of an amp that's flowing between it. It's a really, really small current. Whereas a lightning strike has 100,000 amps. And you've probably heard this unit before. It's the ampere, or amps is what we usually call it. It's the unit of electric current. So let's define what electric current is. So we say that electric current is a flow of electric charge, and it's caused by a potential difference. So that's what we talked about last lesson. At the end of last lesson, we talked about this concept of a potential difference. So what does that mean? It's a really hard idea to understand. So when we talk about a potential difference, it just means that there's a place where you have one type of charge, and then there's a place where you have another type of charge or a neutral charge. And so in between these two places, what's going to happen is an electric field will be created. And that electric field points the direction a positive charge would go. So someone just shout out, which way would a positive charge go if it was placed inside here? Which direction would it go?
Down to the ground.
Down to the ground.
Right.
So that's the direction of the electric field. Yep, the electric field points down because a positive charge would move towards the ground. And so what we realize is that what potential differences do is they create electric fields. So they create electric fields. So if you have a place where there's a lot of charge in one place and not a lot of charge in another place, you're going to create this field between those two places because charges create fields. So a potential difference creates an electric field. So now what will happen is if you imagine you've got like these atoms in the air, well, the atoms have a positively charged nucleus and they have negatively charged electrons whirling around them. If you have a sufficiently large enough potential difference, it can actually rip those electrons off the atoms and rip them up into the cloud. And so that's what you're seeing when you're seeing those little feelers that were like coming out like this. That was actually the electrons being ripped off the atoms. So if you remember back to the waves chapter, we said that light, electromagnetic radiation, is created by oscillating charges or by accelerating charges. So that's what's happening is that this really strong potential difference, this it's like a 300,000 volt potential difference between the cloud and the ground, is such a large potential difference that it's able to rip these electrons off the atoms and ionize the air. And then what I mean by ionize is it means that it's, whoa, my light just shut off. I'm really dark in here now. What I mean by ionize is that the atom is no longer neutrally charged because the electrons have been ripped off of it. Okay, then over here, with my sun touching is it's a very similar idea. It's like I don't know which one's positive or which one's negative, so I'm just gonna guess, and I mean I might get it wrong, but I'm just gonna say that my finger is neutrally charged, so I'm not charged. I didn't slide down the slide, but my son, after sliding down the slide, he became positively charged. So I'm just guessing. I don't know what clothing rubbing on a plastic slide would do. So what happens now is we have a place that's neutrally charged and a place that's positively charged. Well, those positive charges, they don't want to be there. And so what will end up happening is it'll end up sucking electrons off my finger. And I'll show you guys a drawing of this later on. What did I do over here? Get out of there. It'll actually take electrons from my finger that are in my atoms, and it'll actually rip them over into his finger. And so that's what you're seeing with that little discharge of that little lightning there, is it's the electrons from my finger being pulled off my finger by his positive charge in his hand. So that's a potential difference. So anytime you have two places that have different amounts of charge, even if they're the same charge, they don't have to be opposite charges. It's just anytime you have a difference in charge between two places, you're going to have a potential difference, and that will cause charges to flow. All right, do you guys have any questions about current, like charge flow, stuff like that?
As humans,
No.
what is the most heavily charged object we might come into contact with in daily life?
In daily life, probably a battery. I mean, a battery has about 5,000 coulombs of charge inside of it that it's capable of releasing. So I'd probably say a battery.
I looked it up, and that number is 6,250 quintillion, and then all the rest.
Oh, this one?
What the 1 Coulomb thing is, yeah.
Oh man, that's just a huge number. Thanks for sharing that, Ben. That's crazy.
Welcome.
Okay, so let's talk about current a little bit more deeply. So there's a equation for current. So current it's the charge over time. Did you have a question? I'm just hearing audio being transmitted. All right, so current is a charge per time. So it's how much charge is passing by in how much time. We could get way more complicated than this, but we're just trying to keep it simple for this class. In IB physics, we do a whole calculation and derivation of this. But for now, we just need to realize that the reason why, so when you have this like strike, like it's a very, very short time. So there's a very small amount of time in a lightning strike. That's going to give you a really high current. Also, there's a lot of charge in a lightning strike, 15 coulombs. That's also going to give you a high current. So current is basically saying how quickly is the charge passing by. That's what current tells us. So the unit of current is the coulomb per second. So that's the unit of current. It's how many coulombs of charge are passing by per second. So you can just think of these little charges and they're just like flying past. They're just moving along. And we're just saying, hey, how many of those charges are passing by a point per second? And that's going to give you the current. It's how many coulombs of charge pass by in a second. So if you have 100,000 amperes, that means in 1 second, 100,000 coulombs of charge is passing by. And so given that an electron, 1 coulomb is that many electrons, 100,000 coulombs per second is a lot of electrons passing by, like a ridiculously large number of electrons. So I recognize that charge flow and just electricity in general can be a really difficult concept to understand. And so I thought I would take a moment and just sort of through analogy, go back to something that we all really, really understood really well. And that is heat flow. So you'll remember we talked about if you have two objects where one object is hot and the other object is cold, and you bring them together, then what will happen is you have a difference in temperature. So if you have a hot place and a cold place, then what's going to happen with a hot place and a cold place? You guys remember what will happen?
Temperature will flow until they reach thermal equilibrium.
Temperature flows?
I meant heat.
Yeah, so energy is going to flow between them. So energy will flow. So this was because of the law of entropy, right? That as time passes, the energy is going to get more spread out. It doesn't like all the energy to be clumped into one object. The energy wants to spread out. And so it's the same thing that's true for charge. Charge doesn't like to be all clumped together in one place. Charge wants to spread out. It wants to reach that equilibrium state. And so it's the exact same thing that's going on, is that there's this phrase that we say is like nature abhors a gradient. So like nature doesn't like things to be different. It likes things to be equal. That's the law of entropy. So just like how heat flows from hot to cold because of a temperature difference, we can say that charge will flow because of a potential difference, because of this difference in charge between two places. So here's an animation that I created that I'll show you guys. So we could talk about like a hot and a cold object. We could also talk about a positively charged object and a neutrally charged object. So I'm just going to play the animation. So if we take these two objects and we bring them together, there'll be a discharge, and then charges will flow between them until they're equally charged. So I'll play that one more time. So the thing that's kind of weird here is that the neutrally charged object doesn't mean that it has no charges in it. It just means that there's an equal amount of positive and negative charge. Since this object has an excess positive charge, when we bring it into contact with the neutral charge, it's going to actually pull electrons off those atoms and bring them over and then neutralize some of the atoms in this one. And so then you end up having an equal amount of charge across both objects. So charge flows to try to equalize the charge between the two objects. Questions?
So will protons never leave the object? Will it always be electrons that leave?
Right. So in conductors, the electrons are the ones that are freely moving around. So when you have a conductor like a metal, yeah, it's always going to be the electrons that move. But there are other substances, like in particular, I'm thinking about plasma. So in a plasma, the positive ions will move around. But when you're just talking about conductive electrons, like with metals, yeah, electrons are the ones that move around, but it's not always going to be the case. And just think about it like that. It's like the electrons are way smaller, they're way further out, they're able to move more readily than the protons are, or I should say the nucleus is. Does that make sense?
Yep.
Yes, your brain is exactly in the right place. It's the electrons that move around. In IB physics, there's actually this really famous experiment. We talk about it. It's called the Tolman-Stewart experiment that proved that the electrons are the charges that move around. But I think it's a little bit more advanced than I want to talk about in this class. Okay, so I just want you to remember that heat flow, and charge flow are very similar concepts. So heat flows, but what causes heat to flow? It's a difference of what causes heat to flow?
Temperature?
It's a temperature difference. let's call it temp difference. But then charge flows because of a potential difference. So over here, when we have heat flow, we'll have a place that's hot, and we'll have a place that's cold, and the heat will flow between them. Whereas with charge flow, we have a place that's positively charged and a place that's neutrally charged, and then the electrons will flow towards the negatively charged, the positively charged place. So the positively charged place will rip electrons off the neutrally charged place and then transfer that charge between them. It's actually kind of weird. If you look at lightning, like when you look at these slow motion videos, these aren't quite slow motion enough. But if you look really closely, you can actually see that the lightning actually comes from the ground up, that the lightning actually goes up towards the cloud. And that's really hard to see. You have to look at a really, really slow motion video in order to notice that. All right, so the question is, what can we do with this? So now that we know that charges can move around and we can sort of cause them to move around with a potential difference, then what can we do with this? So the idea is that we can light up light bulbs, we can make machines move, we can rotate motors, we can do all sorts of really cool stuff with it. But instead of a burst of charge, what we need is we need a sustained current. So instead of just dumping all that energy all at once, like in a lightning strike, we want to slowly, gradually release that energy. And so in order to do that, we need to control the potential difference. We need to get like a steady, like regulated, controlled temperature difference where it's never able to neutralize, like it's never able to equalize itself, that it never reaches an equilibrium. Well, eventually it will, it has to, but we try to prolong the time it takes to reach that equilibrium. And so that device is called a battery. So here's a schematic of how a battery works. You guys do not need to know all the intricate details of how a battery works. In fact, you can kind of just think of a battery as like a black box. All that a battery does is it separates charge. So there's a chemical reaction that's taking place. You have a chemical reaction. And what it's going to do is it's going to pull, this chemical reaction is going to happen, and it's going to pull negative charges to one side of the battery. So these negative charges get pulled down here. And as those negative charges get pulled to one side of the battery, what's going to happen to the other side of the battery? If all the negatives are getting pulled down, then what's going to be left over on the other side of the battery? Just a question for you guys.
Positive charges.
You're going to have positive charges left over on the other side. So what's doing the work here, that's actually pulling those electrons, it's actually separating them from each other. What's doing the work are the electrical forces within these chemical reactions. So there's chemical reactions that are taking place. So you have chemical energy through these atoms and how they're interacting with each other. That chemical energy is released and turned into electric potential energy. And that's what's creating the separation of charge. Now, what if you don't plug in the battery, it will actually leak out into the air. And the reason is because water molecules, they're actually, I always get this wrong, but I think one side of the water molecule is positive and the other side is negative. I might have totally messed it up. But when there's water vapor in the air, it can actually cause those electrons to be pulled off and go out into the air. And so the charge can actually leak off the battery. So the battery is always creating the separation of charge. So you want to make sure that you're storing batteries in a cool, dry place. You don't want there to be any water vapor around because the charges can actually leak out onto the air. Like if you had a negative charge here, it'd actually be pulled and attracted to the water. So you want to make sure that batteries are not stored in a wet place. This is why it's a really bad idea to put batteries in a freezer. For some reason, people used to think that if you stuck batteries in a freezer that it would like for storage, it would like make them last longer. That's exactly the opposite of what happens. They will drain more quickly. All right, so what we say is happening here is that when we pull these charges and we separate them from each other, what you're creating is you're creating a potential difference. So there's a potential difference across the terminals of this. These are called the terminals. The ends of the battery are called the terminals. So there's a potential difference created across the terminals of the battery. So my question is, what happens if we take a wire? And so that's what you're seeing here. So what happens if we take a wire and we connect the wire? Now, wires are conducting materials. What happens if we connect the wire across the terminals of this battery? So what'll happen? Do you guys know what happens? So we've got a potential difference.
Does current make?
That's exactly. Yep.
Does current be?
Sounds like I'm having some connection issues. Let me check. No, I'm looking pretty good here. Yeah, the potential difference is going to create a current. So what's going to happen is you're going to get current flows. Current in the wire. So that's current is charge flow. So current in the wire means charge flows in the wire. So what will happen is the free electrons in the wire, so the wire is full of free electrons, which we're going to talk about right down here. So before you connect the wire across the potential difference, the wire looks like this. You got all those free electrons are just kind of randomly moving all over the place. So like, maybe one's moving this way. These are the electrons that are freely moving around. They're just randomly flying all over the place. There's really no pattern to this. They're just kind of flying everywhere. Just random motions, like in a gas. These things are just flying all over the place. But as soon as we connect the wire, this is just what I'm looking at is like a small section of the wire. Like imagine you're just zooming in and looking at that part of the wire right there. So what happens is if you connect that wire, so you put the negative side over here, and then you put the positive side over here. If you connect that wire across the terminals of the battery, what will happen is an electric field will be created inside the conductor. And that electric field is pointing to the right. And so what's going to happen to all those electrons? Remember, the electrons have negative charge. What's going to happen to all those electrons if they're inside this electric field? What are they going to do? What are the electrons going to do? Which way will they move?
To the left.
They're going to move to the left. So now every single one of these electrons is going to move to the left. And it's that potential difference that's creating the electric field that's forcing and pushing. Because remember, when a charge is in an electric field, it feels a force. And so now all of those charges are going to get pushed towards the positive terminal. And so the electrons are going to be just moving and zipping around through this wire. So the electrons are going to move through the wire. And then as they move through the wire, they're going to be carrying energy, which can then power or light up the light bulb. And so that's how we're able to get energy out of this, is we're actually taking the energy of those electrons that are moving and we're dumping it to the bulb, and then the bulb's going to light up from that energy. What questions do you guys have for me about this? Okay, we're good. So the free electrons are pushed in the same direction creating a current in the wire. So that's how batteries are able to drive electricity, or to push and drive electrons through a wire. So that's essentially what electricity is, when in the sense that you've probably heard it your whole life, is it's this pushing of charge through a wire. You can almost think of the wire like a pipe, and that the charges are like water and you're like pushing it through the pipe. So the battery is kind of like a pump, and it's like giving it that oomph, and it's pushing it, and it's pushing the charge through the pipe like it pushed water through a pipe. It's a very similar way to think about it. In physics, we usually call this potential difference. We call it a voltage. So when you look at a battery, when you have like the positive side and the negative side of a battery, we'll call that a potential difference. So we'll say from here to here, there's 1.5 volts. So an alkaline battery like this has a potential difference of 1.5 volts. Now people get kind of like tired of saying potential difference, and so people just started calling it volts. They started calling it voltage, and named after the unit. And so the quantity is technically called the potential difference, or rather the electric potential difference, but we end up just calling it the voltage because it's easier to understand. What the voltage tells you is it tells you roughly how much energy you can give to a Coulomb of charge. So when I say that this battery is a 1.5 volt battery, what does that mean? So what it means is that if you have a Coulomb of charge passing from one terminal to the other terminal, so if I have 1 Coulomb of charge moving along this wire. I'm gonna draw all the charges here. If I have a Coulomb of charge, remember how many electrons it is? It's like that. Ben, do you remember the number? It was like that ridiculously huge number. What was it again?
Six 6,250,000,000,000, and then there's always the zeros, so whatever.
So when that many electrons flow through the wire from one terminal to the other terminal of the battery, from one end to the other end of the battery, it'll be roughly 1.5 joules of energy that were supplied to it. So when you say 1.5 volts, it means 1.5 joules of energy is given to 1 Coulomb of charge that flows across the terminals. So there you go. So the voltage is basically telling you how much energy you're able to supply to each Coulomb of charge. That's voltage. So the amount of current that flows in a circuit, it doesn't just depend on the voltage. I mean, it makes sense, right? If I like swapped out a 9-volt battery, there'd be more energy, and so my light bulb would light up brighter. But that's not the only thing that the amount of current depends on. So like you could push the charges harder and they'll flow more easily. They'll flow faster and you'll get more power out of this thing. But there's also this concept called electrical resistance. So I just want to show you guys this animation. This is from that simulation I shared with you a couple of classes ago. So here's our battery and then our light bulb. And so you can see that once we've connected the battery or this is a conducting path. Like even within the light bulb itself, there's still a conductor in there. It's called the filament. But all of this is conductors. And conductors always have those free electrons that are able to move around. So by connecting that path, that conducting path across the terminals of the battery, it's allowing charge to move through the conductor. And then those charges, those electrons are moving through the circuit. So that's the visualization of what's going on there. So we can make these things move quicker, which is current. We can make a greater amount of charge pass each second by using a more powerful battery, like using a higher potential difference battery, maybe like a 9-volt battery or a 12-volt battery. But the other way we can make the current flow more quickly is if we change the material. And so every material they use, every conductor is going to have a certain level of difficulty for the charges to flow through it. And so this concept is called electoral resistance. So remember that idea of like these free electrons inside the conductor? Well, realize that they're moving, and the conductor itself also has atoms in it. And so when you imagine like here's what a wire looks like if you're like zoom it in. So I'm going to look at like one little section of this wire here, and I'm going to zoom in on it. And so we'll see that this side is the positive side of connected to the positive side of the battery, and then this is the negative side. And so the electrons are all zoom in to the left towards the positive side. But notice that they don't have a perfectly clear path, that those electrons can actually bonk into the atoms that are in the conductor. We call those the lattice atoms. So I wish I had an animation of this, but I don't. But you just have to imagine that these electrons are like zoom, 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 like they're flying through this thing. And then every now and then an electron will come. It'll come in and it'll be like bonk, and it'll like bump into that lattice atom. And so now what happens? Well, the electron's going to get slowed down because it's going to bonk into the atom. It'll get slowed down, so it'll stop moving, and then energy is going to get transferred to this lattice atom. So what'll happen is every time an electron bumps into a lattice atom, the lattice atom will start to vibrate more. It'll start to pick up more internal energy. And so we know what happens to things when they start to vibrate more quickly. We know what happens to their temperature. So what's going to happen as these electrons bump, knock into the wire? What will happen to the wire?
Heat go hot.
It's going to get hotter. So these lattice atoms are going to slowly start to get bunk, 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 and they're going to slowly start to get hit by these electrons that are zipping through here, and that's going to cause the lattice atoms to heat up. And so the temperature, when this is true whenever you run an electronic device, it always gets hotter. And it's because pushing these electrons through the material is not free. It's going to cost some energy. You're going to lose some energy due to these collisions of the electrons with the lattice atoms. That concept of these collisions is called electric resistance. All right, so the potential source is the battery, creates an electric field. So we have an electric field inside here. The electric field is pointing to the right because a positive charge would go to the right, but it's not positive charges that move, it's electrons. And so that's why the electrons are moving to the left, because they are negatively charged. Negative charges go the opposite direction of the electric field. We talked about that last time. Discuss how this affects the energy of the electrons. So what's happening is the electrons are going to go from going slow, the electrons are going to be going fast. So the electrons gain kinetic energy. So the electric field is going to exert a force on the charges. It's going to speed them up. The electrons are going to gain kinetic energy. But then something happens. What do the electrons do? They bonk into the lattice atoms. So now we've got this fast moving electron, shoom, 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 and it's going to smack into the lattice atom. That will slow the electron down or maybe even make it bounce backwards. And then the lattice atom will actually end up moving. And so the lattice atom will move. But the problem is that the lattice atoms are actually attached to each other. Like they're bonded to each other. They exert forces on each other. So as soon as you move one this way, the other atom is going to pull it back. And so they end up just vibrating with each other instead. So what ends up happening is that the kinetic energy of the lattice atoms go up. So the electrons give kinetic energy to the lattice atoms. And then as we remember, kinetic energy is proportional to temperature. And so this is going to cause the temperature to increase. So the temperature of the wire, which is what the lattice atoms are, the temperature of the wire increases. We call this resistive heating. And so anytime you use an electronic device, like if I touch my computer right now, the back of my computer is like super hot. Anytime you touch something like a phone or a device that's turned on, you will notice that it gets hot. And so that's why we always build fans into those things. So the fans can like push that hot air out and help cool it down so it doesn't overheat or like melt or burn or anything like that. All right, so this is the last thing I want to teach you guys about is just this concept of how difficult it is for charges to flow through a material is called the electrical resistance. And the unit of the electrical resistance is the ohm. And we use the Greek letter omega for that. The Greek letter omega looks like that. So the reason we don't, it's named after a dude named George Ohm. George Ohm, who's like a German physicist who figured all this stuff out. And we don't want to use O because what if it said, oh, the resistance is 100 ohms. So, if I wanted to say it was 100 newtons, I would just write 100 N. But if you try to do that for ohm, you're like, all right, 100 O. Well, now that doesn't look like a unit. It looks like you just wrote 1,000. So we can't use capital O. So we usually instead use this, which is the last letter of the Greek alphabet. It's the omega, and we use that to represent ohms. Okay, that's it. So I'm just going to give you guys a quick little preview here of the next lesson, which is going to be on a thing called Ohm's law. And Ohm's law is an equation. It says V equals IR. So V is the voltage, I is the current, and R is the resistance. And so the way to think about this is that the voltage is the pump. It's pushing the currents through the circuit. This little pipe here represents the wire. So the voltage is that pump that's pushing the charge through. And then ohms, that's the resistance. So the resistance is ohms up there. And so ohm, you can see he's kind of constricting, he's squishing this pipe so that the charge can't flow as well. And then the I is how quickly the charges are actually able to flow through the circuit. And so there's a relationship between those quantities. If you push harder, you get more flow. If there's a greater resistance, if the pipe is more constricted, then you're going to get less current. And so there's all these relationships, and that's what we're going to be looking at in our next lesson. And there's a lot of math that we're going to do and stuff like that. And that's it, unless you guys have any final questions for me. All right. Have a great day. I'll see you guys later.